Hey, what's up, guys? Okay, so today I'm gonna to talking about the so-called weak law of large numbers, and I guess this is like maybe in your high school or something that you already heard about this theorem, but in this video is rigorous proof it. Okay, so the statement basically say that you have this is theorem. So basically, you have let's say ID random variable is x1, x2 up to xn. Okay, ID. And you want to let's say with they are same right with mean sigma, sorry mean mu and variance sigma, sorry sigma squared. Okay, and so basically this means that the mu and sigma should be well defined, and then you can define xn bar, which is x1 up to xn divided by n. Okay, so you just add all these random variable, and so weak law of large number basically says that this random variable is average of this ID variable, right? So as n goes to infinity, so intuition. So where our intuition should says that if n goes to infinity, then all xn bar should goes to mu. Okay, should go as so goes to this average, right? And rigorous say that so this for all epsilon greater than 0, if you ask the probability of xn bar minus mu is greater than epsilon, so this given n, right? Given any n, this is a number, right? So as limit of n goes to infinity, so n goes to infinity, this number will goes to 0. Okay. So you fix n, this is number as function of epsilon and function of n, and as n goes to infinity, then this guy goes to 0. So this is the weak law of large numbers. Okay, so proof basically very simple. So the idea using Chebyshev inequality. Okay, so if I misspelling, forgive me. Okay, I will quickly prove the Chebyshev inequality if this is the first time you see it, but let me just say the results. So it says that if any random variable is x minus its variant, minus its exponential value, absolute value greater or equal to k of sigma, so k of the standard derivation. So sigma of this variable x, this quantity should be less or equal to 1 over k squared. So this basically says that anything which is larger than k times the standard deviation should at most have 1 over k squared. Okay. Okay, so as this we can prove it, right? So let's compute the expectation value of this xn bar. So it's very trivial, right? Just expectation value of x1 up to xn divided by n. So it's 1 over n times mu, right? Things are all same, so it's the same mu. Okay. And what is the variance of this x1 up to xn? So notice there are ID variable, right? Independent. So it's 1 over n squared, n times variance of x. Okay. So it's variance x divided by n squared. So as my sigma squared divided by n squared. Okay, so we can plug everything in. Sorry, it's 1 over n. Okay. So this means that probability of x n bar minus expectation value of x n bar, which is mu, greater or equal to, sorry, absolute value greater than equal to k times sigma, right? So it's, let's say epsilon is less or equal to, so now k of sigma squared divided by n is epsilon. Okay, so now k is n epsilon divided by sigma squared. Okay, so that means that what we are doing is 1 over k squared, right? So it's n square. Okay, hopefully it's you can write as so. Oh, well, let's see. So n square variance. Oh, sorry, I'm stupid. Yeah, sorry, I missed the factor. Okay, because now because we are doing the k sigma, right? So k sigma here is the square root of it, right? So it's k sigma divided by square root of sigma divided by n, right? Because this is the variance of x bar x and bar this is variance of xn bar, which is the standard deviation of xn bar squared. Okay, so this means that k times square root of sigma divided by n should be equals to epsilon. Okay, so k should be epsilon square root of n divided by square root of sigma. So this is less equal to 1 divided by epsilon square n sigma. Okay, so all these are fixed number, right? All these are fixed number. So if you fix epsilon as n goes to infinity, so as n goes to infinity, then you can see the right hand side goes to 0 because sigma and the epsilon are a fixed number. Okay, so let's prove the results. Okay, so let me just quickly mention how the Chebyshev inequality comes out. Okay, so let's recall the proof of the Chebyshev inequality. Also, which is right. So all the like probabilities start from this Markov inequality. Okay, so probability, let's say any random variable which is greater or equal to 0, if x greater or equal to a, is bounded by an expectation value of x divided by a. So hopefully this is like very easy to understand, right? This means that if your random variable is greater or equal to 0, and you know its expectation value, then you should not deviate from its expectation value too much. And then this proof just one line. Okay, so you can this proof just one line. You can just show that you just do this, right? You can say that prob x greater or equal to a. Let's say you times here. Okay, so you can, let's say this is identity indication function of x greater or equal to a. Okay. So if x less or equal to a, then this inequality, the right hand side is 0, and the left hand side is always true. And if a is greater or equal to 0, then this is still true. And then you take expectation value on both sides, then you get expectation value of x greater or equal to a of expectation value of this, which is probability of x greater or equal to a. So you prove this result. Okay, and now let's quickly prove the Chebyshev. So the proof basically goes as this way, right? So you know that you can start from x minus its average square divided by k squared sigma squared. And then you know that this number, right? To say, okay, so this number is greater or equal to the probability of x minus mu greater or equal to k sigma. And yeah, so these two is basically a definition. You can just, if, yeah, okay. Now this is less or equal to the Markov, right? Because now this is greater or equal to 0. So it's potential value of x minus mu squared divided by k squared sigma squared. And by definition, this number is just sigma squared, right? By definition, this is variance squared. Sorry, the standard deviation squared, which is variance, so it's 1 over k squared. Okay, so it's amazingly this law of large number is almost trivial proof, right? Once you know this Chebyshev inequality, because you can see it's very simple, right? You just write out all the proof. It's less than in 5 minutes, right? So it's almost trivial. Okay, so law of large number is almost trivial, and see you guys next videos.